Alright, silly people, here's the situation. We have a differential equation, which happens to be Legendre's differential equation. We're going to be doing some funny things with it. The first thing that we're going to do is assume that it has a power series solution. F of x equals sum on n to infinity of a sub n x to the n, right? Uh, that's a pretty standard solution to it. And we're going to get a relationship between the constants a n for for recursion purposes. So we're going to do that by actually plugging it into the differential equation bit by bit. First by taking the first derivative and saying that it's clearly the sum on n to infinity of n times a sub n times x to the n minus 1. And then also take the second derivative, dx squared, which is also a pretty easy little derivative to do. It's n times n minus 1 a sub n x to the n minus 2. Now, the problem is that we have to evaluate the term 1 minus x squared d squared f dx squared. So we want everything in the differential equation to be in powers of x to the n, not have any other terms, so otherwise we won't be able to cancel anything out. So we're going to have to find a different way to put d squared f dx squared. And I'm going to claim some pretty wild things, so buckle your seatbelts. What we're going to do is, first of all, we're going to notice that this sum here is 0 for the first couple values of n, because if you plug in n equals 0, you have a whole thing multiplied by 0. And then if you plug in n equals 1, you have the whole thing multiplied by n minus 1, so 1 minus 1 is 0, so another 0. But then you have every other term, so it's n equals 2 to infinity times n minus 1 a n x n minus 2. That's kind of crazy. So a sum from 0 to infinity is actually a sum from n equals 2 to infinity. Well, we definitely want it to be a sum from 0 to infinity, though, so that we can stick it back in the equation and get everything, have everything be the right sum. So what we can do is we can rewrite the sum, just putting the 2 on the other side of the equal sign, and be like, this is n minus 2 equals 0 to infinity of n minus 1 a n x to the n minus 2. Now we can cleverly define a variable m to be n minus 2, so that this is a sum on m from 0 to infinity of, and then given this definition, n is going to be m plus 2, n minus 1 has become m plus 1, a sub n becomes a sub n plus 2, or m plus 2, I guess. So m plus 2, and then it's x to the n minus 2 becomes x to the m. Fantastic. And then at this point, you can quote Shakespeare and say, what's in a name? That which we call an m by any other name would smell as sweet, especially if we called it n. So you can write this instead as n plus 2, n plus 1, n plus 2 here, and x to the n. And now we have a sum on n of x to the n again. Fancy stuff there. So now when we write 1 minus x squared d squared f dx in the differential equation, we can use the this expansion of the term for the first term in there, so it's going to be a sum on n to infinity in brackets n plus 2, n plus 1, a n plus 2, x to the n, minus x squared, and then for the x squared term you actually use the first form of the equation that we got. So this is also a sum on n to infinity but this is times n and minus 1 x to the n minus 2, and also a sub n. So now the x squared is going to cancel out the minus 2 and the x there. So we actually have something that only depends on x to the n, which is why we did this whole rigmarole in the first place. X to the n, and I'm going to stick it actually out here. Awesome. But we have the rest of the differential equation to take care of to get our nice little recursion relation. So let's pick this up and plop it down next to, we also need minus 2x times df dx, which we found was n times a sub n times x to the n minus 1. And let me put a big brace here so that we know that we're summing all of these over n. So it's n a n x n minus 1, and then it's also plus l by l plus 1 times f, which again is just a n x to the n. And then the whole thing is equal to 0. Awesome. We can simplify that a bit because you're going to factor the x through into here. Oh, and also because we're summing, it's the same sum everywhere, so it's essentially not a sum anymore. The whole thing is going to go to 0. So we can just keep this part proportional to x to the n that we got going on right here, minus 2 n a sub n. This x cancels out this minus 1, so it's just x to the n here as well. This is also just x to the n. So let's cancel out all the x to the n's and rewrite the equation with, let's put all the stuff which depends on n a sub n to the right hand side. So we're going to have n plus 1, n plus 2, a n plus 2 equals n by n minus 1 a sub n. I'm going to stick that at the end actually, put this all in a big braces. A smaller big braces though. N by n minus 1 plus 2n minus l by l plus 1 all times a sub n. So now just complete the algebra and put the stuff which is on the left hand side over on the right hand side. So you have n plus 1, n plus 2, a n. And at this point you're going, oh, this isn't a recursion relation, this is a reverse recursion relation. It's telling you the constants in the future, not the ones in the past. And you're right, which is why we should just take n to n minus 2, right? So on the left side, this is going to be an. On the right hand side, this is going to be n minus 2 minus 1, plus 2 times n minus 2, minus l by l plus 1, all over, and this is going to be, let's say, n minus 2 plus 1, n minus 2 plus 2, all times a n minus 2. Cool stuff. Let's simplify stuff a little bit before we start expanding it. N minus 2 times n minus 3 plus 2n minus 4 minus l by l plus 1 all over, n minus 1 times n, just n. Okay, and that's times an minus 2. Let's expand that guy out now so that you have n squared minus 2n plus 6 minus 3n. So It's actually minus 5n total. Let's write that instead. Plus 2n minus 4 minus L by L plus 1 all over n by n minus 1, an minus 2. Okay, simplifying even further, we have n squared minus 3n. Oh, and that's actually plus 6, my bad. Plus 2 minus L by L plus 1 all over n by n minus 1, an minus 2. I'm going to tell you that this has some factorizations that you may or may not like, but you can check as an exercise for you that it works, because it can go like L minus n plus 2 times L plus n minus 1 with a minus sign all over n by n minus 1. That is the form that matches the Wikipedia thing anyway, which I thought would be nice to show. So that's it. That's the recursion relation. The next bit of the problem is to argue that unless the series truncates, which can only happen if L is an integer, the solution will diverge at x equals 1. This is kind of just, it may be a no-brainer to some people, but if you have an infinite sum at of a sub n x to the n that never truncates, then f sub 1 of 1 is going to equal a0 plus a1 plus a2 plus a3 plus dot 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 to infinity. And just given this relationship here, the constants are kind of getting larger every time we increase, especially if L is not an integer. The constants are just getting larger and larger and larger. So the thing is going to go to infinity if, x is 1, which is really weird. So L does have to be an integer for you to have a solution to this. At x equals 1, if L is not an integer, then it becomes something called a Legendre function, which is not really the scope of this video. So the next part of the problem is to just write out what the Legendre polynomials are, which are the solutions to this for f even and f odd solutions to this. So what that's talking about is whenever you do expand this, you're going to get a0 plus a1x plus a2x squared plus a3x cubed plus dot dot dot. The series alternates between an even solution and an odd solution. Starts out with an even one, so where the function is just a constant, and then an odd one where it's a line, and then an even one where it's a parabola, and then it's an odd one where it's a cubic function. So the Legendre polynomials are the ones that are, it's telling you which ones are even, which ones are odd, and it's kept in line by the powers of L. So for P0, which is the L equals 0 Legendre polynomial, it's just the first constant. It truncates there. And usually Legendre polynomials are normalized such that it's equal to 1 when x is 1. So that first constant is usually just given 1, right? The first Legendre polynomial, so P1, truncates at a1x. You exclude the first constant because, you only want an odd solution term from it. So that's going to be the first odd term is the one proportional to x. And then we also want this to normalize such that the function is 1 when x is 1. So you set a1 to 1. And then the first Legendre polynomial is just x. The second Legendre polynomial is going to include the first constant plus a2x squared, and that's where it truncates. a2, though, we have a particular little form for it up here via the recursion relation. It's related to a0. So this is a0 minus L is 2, so it's 2 minus n, and 2 happens to be n. So yeah, n happens to be 2, so it's 2 minus 2 plus 2 times 2 plus 2 minus 1 all over 2 by 2 minus 1 all times a0 x squared. So it's a0 times a bunch of stuff. It's 1 minus, and then it's 2 times, let's see, that's 3 over 2 x squared in there. So it's a naught 1 minus, and then it's just 3x squared. Now we want that to go to 1 when x is equal to 1. So if you plug in 1 there, you get 1 minus 3, which is minus 2. So you definitely want a0 to be minus 1 half times 1 minus 3x2. But it's typically written as 1 half of 3x squared minus 1. Okay, then the last Legendre polynomial that we have to write out is P3, which you take the linear term plus the cubic term, and then you use the the recursion formula to figure out what the constant on the cubic term is. I'm already forgetting what the actual recursion formula is, so let me copy it down to reference it here. So it's going to be a1 x cubed times, up here it's going to be 3 minus 3, so 0 plus 2, and then 3 plus 3, so 6 minus 1 is 5. And down here it's going to be 3 by 3 minus 1, so 3 times 2, so 6. Okay, so we got a1 x times 1 minus x squared 5/3. Okay, and then we want this to normalize to be 1 at x equals 1. So if we set x equal to 1, we're going to have a1 times 1 minus 5/3, which is 1 minus 5/3 equals 1 minus 3/3 minus 2/3, so it's minus 2/3. That was some quick maths. So obviously you want a1 to be minus 3/2 to get that, and then I bet it's typically written, and there's an x here, I bet it's typically written as 3/2 x times x squared times 5/3 minus 1. But that's just a guess. Alright.